Oh, hello there. Have you ever thought about how light interacts with atoms? It's a crucial relationship in art, and it can be described with chemistry. So, let's play around with light and make some electrons dance. I'm Matt Queen, and this is Line and Emission Spectra. This lamp gives off what scientists call white light. It's actually made up of all the different colors of visible light. You can see this if we separate those different colors by passing it through a set of diffraction grating glasses. Oh, nothing overly surprising there. But think about the things that we normally call neon lights. They aren't white. In fact, they come in all sorts of different colors. These lamps aren't actually filled with neon. In fact, they're filled with all different gases. That's what gives them their different colors. This lamp is filled with hydrogen gas. Energy's now being pumped into the hydrogen gas. The first thing it does is break apart the hydrogen molecules. Now, there are just individual hydrogen atoms left to absorb the energy. The only way to do that is through their electrons. Negatively charged electrons are attracted to positively charged protons in the nucleus. It takes energy to pull them apart. It's a lot like magnets. The difference between magnets and electrons in atoms is that electrons can only be certain distances away from the nucleus. Those distances all have distinct energies. We can illustrate what we see using an energy level diagram. The electron in a hydrogen atom starts off in the lowest energy level, N equals 1. It can absorb the right amount of energy to be promoted to a higher energy level. For example, N equals 3. The excited electron then transitions to a lower energy level. In this case, from N equals 3 to N equals 2, giving off a red photon with a specific energy and wavelength of 656 nanometers. A different atom might have its electron excited to the N equals 4 energy level. If this electron transitions from N equals 4 to N equals 2, a blue-green photon with a wavelength of 484 nanometers is emitted. Since only certain electronic energy levels are allowed, only photons with specific energies or wavelengths are ever emitted. The photons are quantized as well. Let's explore the implications of this theory by putting the light emitted from our hydrogen bulb through the diffraction grating glasses, just like we did with the white light. Whoa. While the power supply is on, a huge number of hydrogen atoms are rapidly absorbing and emitting energy, and electrons are making all the possible transitions between all the allowed energy levels. Many of the emitted photons have wavelengths our eyes can't even detect. We can see the ones in the visible spectrum, which corresponds to electrons descending to the second energy level, the N equals 2, from the third, which is red, the fourth, which is turquoise, the fifth, which is violet, and the sixth, which is purple. This gives us the entire spectrum of hydrogen. Different elements all have different emission spectra. They're kind of like chemical fingerprints that can be used to identify an element. Some are much more complicated than the hydrogen spectrum, but the general concept's the same. The electrons only have a few allowed energy levels, or distances from the nucleus, and the emission spectrum corresponds to electrons that have been energized to those excited, or higher energy levels, returning to the lower ones. In general, the color of paints can be explained using similar concepts. White light in the room hits the compounds in the paint and is absorbed. The light that's not absorbed hits our eyes and gives us the beautiful colors that we see before us. This type of knowledge takes visits to the art museum to an entirely different energy level. So there you have it. God, does it get any cooler than that?